Hi everyone. So for this week's lecture, we are looking at or reviewing the concept of temperature. So again, as a refresher, temperature is a measure of the average kinetic energy of atoms or molecules in a substance. So again, every object, every matter on Earth has atoms and molecules, and when these molecules vibrate really fast, that means that they have a higher temperature, so the object will get warmer, and when the atoms and molecules vibrate really slowly, then that means the temperature decreased, so the object is cooler, for example. So again, the air consists of gas molecules, so the temperature of the air is a measure of how quickly the molecules are moving, and the more energy of the motion the molecules have, the higher the temperature you feel in the air. And temperatures are recorded daily at thousands of weather stations worldwide, provide much of the temperature data compiled by meteorologists and climatologists. So, what does it mean when we say the daily mean? Well, a location's daily mean temperature is determined by averaging the 24-hourly reading or by adding the maximum and minimum temperatures for a 24-hour period and dividing it by 2. Whereas the daily temperature range, this is the difference between the daily highs and lows. So the method you'll be doing for the daily temperature range, you will be subtracting the highest temperature of that day with the lowest temperature of that day. And then we can do calculations based on longer periods. For example, the monthly mean temperature is calculated by adding together the daily means for each day of the month and dividing by the number of days in the month. And annual mean, this is based on the average of the 12 monthly means. And then the annual temperature range, you'll be subtracting between the warmest and coldest monthly mean temperatures. So mean temperatures are especially useful for making daily, monthly, and annual comparisons. So here we have an image of Death Valley, and the highest accepted temperature record for the US as well as the entire world is 134 degrees Fahrenheit, and this long-standing record was set at Death Valley, California on July 10th, 1913. So again, why are summer temperatures at Death Valley so high? Well, this is due to Death Valley being a desert, and also it is far from the Pacific Ocean, less than 200 miles, and the mountains, the Sierra Nevadas, cut off the valley from the ocean's moderating influence and moisture. And also the clear skies allow the maximum solar radiation to strike the dry, barren surface. Because no energy is used to evaporate the moisture, which occurs in humid regions, all the energy is available to heat the ground through the process of conduction. And here for your first quiz, you were analyzing an isotherm map. So isotherms, what does that mean? Well, this is a line that connects points on a map that have the same temperature. And here we see the isotherm lines across the United States. So to display the distribution of air temperatures over large areas, isotherms are commonly used. So the large map shows high temperatures for a spring day. Isotherms, again, are lines that connect points of equal temperature. And on television and in many newspapers, temperature maps are in color as shown here. In the inset map, and rather than label the isotherms, these maps label the areas between isotherms. For example, The zone between the 60s and 70 isotherms is labeled 60s. So here we have the 60s here. And closely spaced isotherms indicate a rapid rate of temperature change, whereas more widely spaced lines indicate a more gradual rate of change. Now let's look at the cycles of air temperature. So you know from experience that a rhythmic rise and fall of air temperature occurs almost every day. And here we could see the minimum temperatures occur just before sunrise, and the maximum temperature occurs mid to late afternoon. So here, based on this meteogram showing temperatures in Chicago, Illinois, we could see the time on the x-axis, so 6 a.m. to 6 noon, and then 6 p.m. So the temperature dropped at 6 a.m. on Sunday, February 19th, and then the temperature rose to 60 degrees Fahrenheit by afternoon. So we see that pattern here, and the primary control of the daily cycle of air temperature is Earth's daily rotation, which causes a location to move into daylight for part of each day and then into darkness. So again, as the sun's angle increases throughout the morning, the intensity of sunlight also rises, reaching a peak at noon and gradually diminishing in the afternoon. So during the night, the atmosphere and the surface of Earth cool as they radiate away heat, and the minimum temperature therefore occurs about the time of sunrise when the sun again begins to heat the ground. So why do temperatures vary? Well, we're going to look at various temperature controls. And what does temperature control mean? Well, this is any factor that causes temperatures to vary. The primary or number one control of temperature is latitude because it determines the annual variations in sun angle and length of daylight. For our previous lecture, we covered seasons, and we learned that the sun's vertical rays travel between the tropics. So it hits the Tropic of Cancer to the Tropic of Capricorn. And when it hits the Tropic of Cancer on the June solstice, we know we see a longer length of daylight hours in the northern hemisphere compared to the southern hemisphere on June 21st, 22nd. So on that specific day, we have the longest day length on that month. And here we can see on this graph, the data for these 5 cities remind us that latitude is a significant factor influencing temperature. So we could see, let me draw here. We have the equator representing 4 degrees south for Peru. And we could see with the purple line that in Peru, the mean temperature for each month, it is consistent below 80, so high 70s. And that's because the equator receives consistent day length, consistent sun rays, and has consistent day length hours. For example, 12 hours day, 12 hours night. And then we could see as you go farther up in the northern hemisphere, close to the Arctic Circle for Alaska, we could see that there's a large annual temperature range. And it gets in January below negative 28 degrees Celsius, but in the summertime, June, July, the temperature raises to at least 4 degrees Celsius, between 4 and 8 degrees Celsius. And that's due to the low sun angles that the pole receives. And again, we see here, specifically for the northern hemisphere, we have an increase in day length, daylight hours, because the sun's vertical rays are hitting the northern hemisphere. And other important controls of temperature are differential heating of land and water, ocean currents, elevation, the geographic positioning and prevailing winds, as well as cloud cover and albedo. So for elevation, temperatures decrease with elevation, and we know that temperatures decrease in the troposphere layer. And then, like we learned in previous lecture, the second layer above the troposphere is the stratosphere. We know the temperature increases because of the ozone gas. But here we're focused on the troposphere, so temperature decreases as we go higher in altitude, and the atmosphere is thinner at higher elevations, meaning that as you go higher in altitude, pressure decreases, and higher elevations produce a greater daily temperature range, meaning that when at nighttime it drops, the temperature drops to being really cold compared to in the daytime where the temperatures warm up significantly in that area. We have ocean currents, and this map here is showing us the major surface ocean currents around the world. So poleward moving currents are warm and equatorward moving currents are cold. And on this map, we could see the warm currents are represented by a red arrow and the cold currents are represented by a blue arrow. And the surface ocean currents are driven by global winds and play an important role in redistributing heat around the globe. So again, we see the example here of the California current being a cold current, and then we have on the east coast of the United States a warm current known as the Gulf Stream current. So this is mindful to keep in mind of our major ocean gyres around the world. And here in the satellite image of the east coast of the United States, red represents higher water temperatures and blue represents cooler water temperatures. So this current transports heat from the tropics far into the North Atlantic, like we see here. So the transfer of heat by winds and ocean currents is nature's attempt to equalize the latitudinal energy imbalance between the tropics and the poles. And ocean water movements account for about 1/4 of this total heat transport, and winds account for the remaining 3/4. So here we could see the chilling effect of a cold current versus a warm current. The monthly mean temperatures for Rio, Brazil, and Arica, Chile, both are coastal cities near sea level. Even though Arica is closer to the equator than Rio, its temperatures are cooler due to the influence of the Peru current that we see here. And Arica is influenced by the cold Peru current, whereas Rio is next to the warm Brazil current. And here we can see with Arica, the temperatures are below 70s degrees Fahrenheit, whereas with Rio, it's high 70s. So there's a difference there, and we could apply it here for California due to us being nearby a cold current, the California cold current, so we have cooler temperatures compared to the East Coast. Also, the fourth temperature control we have is the geographic position and prevailing wind direction. So if we take a look at this map, we could see the arrows showing us the wind direction, and wind is labeled is based on where it's coming from. So the wind is coming from the west, and this is a prevailing wind. We're in the wind belt of the westerlies. So again, when we're looking at these terms here, windward coast, an example is Eureka, California that we see here, experiences the moderating influence of the ocean. So we have this area has cooler summers and milder winters and a smaller annual temperature range. Whereas the leeward coast at the same latitude, which is New York City, experiences a larger annual temperature range. And we could see that difference here, a large annual temperature range. In January, it's below 30 degrees Fahrenheit, and then in the summertime, June, July, it's above 70 degrees Fahrenheit. So when you subtract 30, close to 30, you have a larger annual temperature range compared to Eureka, California. And here this is a diagram showing us the global wind patterns, and the United States is found in this zone of the westerlies. And we'll learn these pressure systems and the major winds, but for the purpose of this lecture, we just want to look at the influences of these global wind belts. And again, we're continuing on with the same lecture, but prevailing winds can also affect temperatures if the winds blow across a mountain range, where the mountains create a barrier from the moderating effects of the ocean. So in this case, the Cascade Range, which is found here, cuts off Spokane, Washington from the moderating influence of the Pacific Ocean. So Seattle has the influence of the Pacific Ocean compared to Spokane here. And this is known as orographic lifting. So this is the windward side of the mountain, and this is the leeward side of the mountain range. And cloud cover and albedo, while more clouds lower surface temperatures during the day, but cause warmer temperatures at nighttime. So why is that? Well, clouds have a higher albedo, so light colored surfaces have a higher albedo than dark colored surfaces. So during the daytime, when the sun's radiation enters the atmosphere, the clouds will reflect the incoming solar radiation, and that is why clouds have a higher albedo, which will lower the surface temperature. So it will be a cooler temperature during the daytime, but at nighttime it acts as a blanket. So at nighttime, the Earth's radiation will leave and enter into the atmosphere, and then it will get trapped by the clouds, so it could radiate back onto Earth's surface. So again, and albedo, this is just based on reflectivity. So a high albedo reduces surface temperature, like I just mentioned before. And here we could see a graph showing us the effects of cloud cover. Smart figure 3.15, we're looking at the daily cycle of temperature at Illinois for 2 July days, and we could see that with an overcast day, the temperatures are cooler than compared to a clear day. So by the afternoon, we could see it's high 70s, whereas on a clear sunny day, the temperatures can exceed 85 degrees. So also on figure 3.17, we could see the contrasting albedos. So ice and snow covered surfaces have high albedos, thus keeping air temperatures lower than if the surface were not highly reflective. This image shows the Malaspina Glacier in Alaska. So the darker colored surfaces will absorb the heat instead of reflecting it. So lower albedo for the oceans and the dark colored surface there. And then we have the global distribution of temperatures. So here we're comparing two world maps, and these are isotherm maps showing us locations with equal temperature or in the ranges of temperatures. And this map is showing us January, and this one is in July. So what we can see here, the patterns observed on the map is that there is a decrease in temperatures poleward from the tropics. And I don't know if I could zoom in. And also the coldest and warmest temperatures are found over land compared to the oceans, and the isotherms in the southern hemisphere, where there is less land compared to water, are much straighter than in the northern hemisphere. So here we could see the straight line, isotherm lines in the southern hemisphere, and then in the northern hemisphere, due to the land-water differences, we have curved isotherm lines. And warm currents cause isotherms to be deflected towards the poles, whereas cold currents cause an equatorward bending. So the global distribution of temperature, well, the temperature range is smaller at the equator compared to the higher latitudes, as we know, because of the consistent sun angle occurring between the tropics, and the interiors of continents have a higher temperature range and coastal regions have a smaller temperature range because of the moderating influence of the oceans and the specific heat. And what we learned earlier was that land heats up and cools faster than water to have a higher temperature range. This map here is showing us the global annual temperature ranges in Fahrenheit. So again, when you subtract the coldest to the warmest month, temperatures will have a smaller annual temperature range. So along the equator, 5 degrees Fahrenheit is the temperature range. So 85 degrees Fahrenheit, subtract, which would be the hottest month, subtract the coldest month, 80 degrees Fahrenheit, you have 5 degree Fahrenheit temperature range along the equator, let's say. And then as we go higher in latitude by the poles, you can see 90 degrees Fahrenheit temperature range difference. So that is it for our lecture this week, looking at the temperature controls of our planet. And be sure to submit the quiz and your responses to your 2 peers this Friday. Thank you for watching.